Thermal spraying techniques are coating processes in which melted materials are sprayed onto a surface. The feedstock is heated by electrical or chemical means. Thermal spraying can provide thick coatings over a large area at high deposition rate as compared to other coating processes such as electroplating, physical and chemical vapor deposition. Coating materials available for thermal spraying include metals, alloys, ceramics, plastics and composites. They are fed in powder or wire form, heated to a molten or semimolten state and accelerated towards substrates in the form of micrometer-size particles. Combustion or electrical arc discharge is usually used as the source of energy for thermal spraying. Resulting coatings are made by the accumulation of numerous sprayed particles. The surface may not heat up significantly, allowing the coating of flammable substances. Coating quality is usually assessed by measuring its porosity, oxide content, macro and micro hardness, bond strength and surface roughness. Generally, the coating quality increases with increasing particle velocities. Several variations of thermal spraying are distinguished: plasma spraying, detonation spraying, wire arc spraying, flame spraying, high-velocity oxy-fuel coating spraying, warm spraying, cold spraying. In classical but still widely used processes such as flame spraying and wire arc spraying, the particle velocities are generally low, 15,000 K, which makes it possible to spray refractory materials such as oxides, molybdenum, etc. System overview: a typical thermal spray system consists of the following: spray torch, the core device performing the melting and acceleration of the particles to be deposited, feeder, for supplying the powder, wire or liquid to the torch through tubes. Media supply, gases or liquids for the generation of the flame or plasma jet, gases for carrying the powder, etc. Robot, for manipulating the torch or the substrates to be coated. Power supply, often stand-alone for the torch. Control console, either integrated or individual for all of the above. Detonation thermal spraying process. The detonation gun consists of a long water-cooled barrel with inlet valves for gases and powder. Oxygen and fuel is fed into the barrel along with a charge of powder. A spark is used to ignite the gas mixture, and the resulting detonation heats and accelerates the powder to supersonic velocity through the barrel. A pulse of nitrogen is used to purge the barrel after each detonation. This process is repeated many times a second. The high kinetic energy of the hot powder particles on impact with the substrate results in a buildup of a very dense and strong coating. Plasma spraying. In plasma spraying process, the material to be deposited typically as a powder, sometimes as a liquid, suspension or wire is introduced in the plasma jet, emanating from a plasma torch. In the jet, where the temperature is on the order of 10,000 K, the material is melted and propelled towards a substrate. There, the molten droplets flatten, rapidly solidify and form a deposit. Commonly, the deposits remain adherent to the substrate as coatings. Freestanding parts can also be produced by removing the substrate. There are a large number of technological parameters that influence the interaction of the particles with the plasma jet and the substrate and therefore the deposit properties. These parameters include feedstock type, plasma gas composition and flow rate, energy input, torch offset distance, substrate cooling, etc. Deposit properties the deposits consist of a multitude of pancake-like splats called lamellae, formed by flattening of the liquid droplets. As the feedstock powders typically have sizes from micrometers to above 100 micrometers, the lamellae have thickness in the micrometer range and lateral dimension from several to hundreds of micrometers. Between these lamellae, there are small voids, such as pores, cracks and regions of incomplete bonding. As a result of this unique structure, the deposits can have properties significantly different from bulk materials. These are generally mechanical properties, such as lower strength and modulus, higher strain tolerance, and lower thermal and electrical conductivity. Also, due to the rapid solidification, metastable phases can be present in the deposits. Applications This technique is mostly used to produce coatings on structural materials. Such coatings provide protection against high temperatures, corrosion, erosion, wear. They can also change the appearance, electrical or tribological properties of the surface, replace worn material, etc. When sprayed on substrates of various shapes and removed, freestanding parts in the form of plates, tubes, shells, etc. can be produced. It can also be used for powder processing. In this case, the substrate for deposition is absent and the particles solidify during flight or in a controlled environment. This technique with variation may also be used to create porous structures, suitable for bone ingrowth, as a coating for medical implants. A polymer dispersion aerosol can be injected into the plasma discharge in order to create a grafting of this polymer onto a substrate surface. This application is mainly used to modify the surface chemistry of polymers. Variations equals, plasma spraying systems can be categorized by several criteria. Plasma jet generation, direct current, where the energy is transferred to the plasma jet by a direct current, high-power electric arc, induction plasma or RF plasma, where the energy is transferred by induction from a coil around the plasma jet, through which an alternating, radio frequency current passes, plasma-forming medium, gas-stabilized plasma, where the plasma forms from a gas. Typically argon, hydrogen, helium or their mixtures, water-stabilized plasma, where plasma forms from water or other suitable liquid, hybrid plasma, with combined gas and liquid stabilization, typically argon and water, spraying environment, air plasma spraying, performed in ambient air, controlled atmosphere plasma spraying, usually performed in a closed chamber either filled with inert gas or evacuated, variations of CAPS, high-pressure plasma spraying, low-pressure plasma spraying, the extreme case of which is vacuum plasma spraying, underwater plasma spraying. Another variation consists of having a liquid feedstock instead of a solid powder for melting. This technique is known as solution. Precursor plasma spray vacuum plasma spraying Vacuum plasma spraying is a technology for etching and surface modification to create porous layers with high reproducibility and for cleaning in surface engineering of plastics, rubbers and natural fibers as well as for replacing CFCs for cleaning metal components. This surface engineering can improve properties such as frictional behavior, heat resistance, surface electrical conductivity, lubricity, cohesive strength of films, or dielectric constant, or it can make materials hydrophilic or hydrophobic. The process typically operates at 39°-120 degrees Celsius to avoid thermal damage. It can induce non-thermally activated surface reactions, causing surface changes which cannot occur with molecular chemistries at atmospheric pressure. Plasma processing is done in a controlled environment inside a sealed chamber at a medium vacuum, around 13°-65 pascals. The gas or mixture of gases is energized by an electrical field from DC to microwave frequencies, typically 1°-500 W at 50 V. The treated components are usually electrically isolated. The volatile plasma byproducts are evacuated from the chamber by the vacuum pump, and if necessary can be neutralized in an exhaust scrubber. In contrast to molecular chemistry, plasmas employ molecular, atomic, metastable and free radical species for chemical effects. Positive ions and electrons for kinetic effects. Plasma also generates electromagnetic radiation in the form of vacuum UV photons to penetrate bulk polymers to a depth of about 10 micrometer. This can cause chain scissions and cross-linking. Plasmas affect materials at an atomic level. Techniques like X-ray photoelectron spectroscopy and scanning electron microscopy are used for surface analysis to identify the processes required and to judge their effects. As a simple indication of surface energy, and hence adhesion or wettability, often a water droplet contact angle test is used. The lower the contact angle, the higher the surface energy and more hydrophilic the material is. Changing effects with plasma at higher energies ionization tends to occur more than chemical dissociations. In a typical reactive gas, 1 in 100 molecules form free radicals whereas only 1 in 106 ionizes. The predominant effect here is the forming of free radicals. Ionic effects can predominate with selection of process parameters and if necessary the use of noble gases. Wire arc spray. Wire arc spray is a form of thermal spraying where two consumable metal wires are fed independently into the spray gun. These wires are then charged and an arc is generated between them. The heat from this arc melts the incoming wire, which is then entrained in an air jet from the gun. This entrained molten feedstock is then deposited onto a substrate. This process is commonly used for metallic, heavy coatings. Plasma transferred wire arc equals. Plasma transferred wire arc is another form of wire arc spray which deposits a coating on the internal surface of a cylinder, or on the external surface of a part of any geometry. It is predominantly known for its use in coating the cylinder bores of an engine, enabling the use of aluminum engine blocks without the need for heavy cast iron sleeves. A single conductive wire is used as feedstock for the system. A supersonic plasma jet melts the wire, atomizes it and propels it onto the substrate. The plasma jet is formed by a transferred arc between a non-consumable cathode and the type of a wire. After atomization, forced air transports the stream of molten droplets onto the bore wall. The particles flatten when they impinge on the surface of the substrate, due to the high kinetic energy. The particles rapidly solidify upon contact. The stacked particles make up a high wear-resistant coating. The PTWA thermal spray process utilizes a single wire as the feedstock material. All conductive wires up to and including 0.0625 inches can be used as feedstock material, including cord wires. PTWA can be used to apply a coating to the wear surface of engine or transmission components to replace a bushing or bearing. For example, using PTWA to coat the bearing surface of a connecting rod offers a number of benefits including reductions in weight, cost, friction potential, and stress in the connecting rod. High-velocity oxygen fuel spraying. During the 1980s, a class of thermal spray processes called high-velocity oxy-fuel spraying was developed. A mixture of gaseous or liquid fuel and oxygen is fed into a combustion chamber, where they are ignited and combusted continuously. The resultant hot gas at a pressure close to 1 bar emanates through a converging diverging nozzle and travels through a straight section. The fuels can be gases or liquids. The jet velocity at the exit of the barrel exceeds the speed of sound. A powder feedstock is injected into the gas stream, which accelerates the powder up to 800 meters per second. The stream of hot gas and powder is directed towards the surface to be coated. The powder partially melts in the stream, and deposits upon the substrate. The resulting coating has low porosity and high bond strength. HVOF coatings may be as thick as 12 millimeters. It is typically used to deposit wear and corrosion-resistant coatings on materials, such as ceramic and metallic layers. Common powders include WC-CO, chromium carbide, macrolide, and alumina. The process has been most successful for depositing ceramic materials and other corrosion-resistant alloys. Cold spraying. In the 1990s, cold spraying was introduced. The method was originally developed in Russia, with the accidental observation of the rapid formation of coatings. This occurred while experimenting with particle erosion of a target exposed to a high-velocity flow loaded with fine powder in a wind tunnel. In cold spraying, particles are accelerated to very high speeds by the carrier gas forced through a converging diverging DeLaval-type nozzle. Upon impact, solid particles with sufficient kinetic energy deform plastically and bond mechanically to the substrate to form a coating. The critical velocity needed to form bonding depends on the material's properties, powder size and temperature. Metals, polymers, ceramics, composite materials and nanocrystalline powders can be deposited using cold spraying. Soft metals such as Cu and Al are best suited for cold spraying, but coating of other materials by cold spraying has been reported. The deposition efficiency is typically low for alloy powders, and the window of process parameters and suitable powder sizes is narrow. To accelerate powders to higher velocity, finer powders,